Howdy! Today we're going to look at arc length. We're going to determine how to find out what the length of a curve is in the XY plane. Okay, so let's get started here. Suppose we have the simplest possible curve. Let's just say it's the straight horizontal line from say 1 to 8. Okay, what would be the length of that curve going from 1 to 8? Easy enough. 8 minus 1 is 7, right? Not a big deal at all. So that one's easy. Let's try something a little bit harder. What about, let's take the function f of x is equal to, say, 5x plus 1, and say we're on the interval from 1 to 3. Okay, so it's going to look something like this. It's going to be a line which looks something like this. And here you are at 1. Here you are at 3. The value of this point is what? 1/6. Agreed? And the value of this point is going to be 3, what? 15/16. Agreed? And so what do we want? We want the length of this curve right there. If you were to walk along that curve, how long would you walk? Well, Pythagorean theorem, right? 16 minus 6 is 10. 3 minus 1 is 2. So the length, use a script L for the length, would be just 2 squared plus 10 squared is the square root of what? 104? Square root of 104. So can you reduce that at all? That's 104 is the same as 52 times 2, which is the same as 26 times 4. And you can bring the 4 outside. 2 times the square root of 26, right? 2 times the square root of 26. So there's the length. Okay? Not bad. But, of course, the whole point of calculus is being able to do problems that you can't do just with geometry and algebra. So now, let's suppose that we've got some typical generic looking curve similar to what I've been putting up here before, from A to B. And so here's the function y is equal to f of x. And we want to figure out what's the length of this curve. If you were to walk along it, what's the length of this curve? Well, we're going to do something very calculus, with a real calculus feeling here. Hopefully you'll agree. What we're going to do is we're going to take a little segment of it, just like we took little segments of rectangles and things like that in the previous problems. Here we're going to take a little segment, and this is going to be a little delta x right there between these 2 points. This is a little delta y right there. And so would you agree with me that the curve there is going to be somewhat close to the hypotenuse? And of course the length of the hypotenuse, similar to what we just did in the previous problem, is going to be delta x squared plus delta y squared. There's the length of it, right? Is delta x squared plus delta y squared. There's the length of the hypotenuse. And it seems reasonable, it looks like, that the length of that hypotenuse is going to be similar to the length of the arc there. And as you get smaller and smaller, make a smaller and smaller triangle, this hypotenuse is going to be closer and closer to the length of the arc. Now, by the way, as soon as I do that, I get feeling a little bit guilty because I'm appealing to your intuition. I'm appealing to your kind of just intuitive sense of what curves look like. This is the kind of mathematics that was done by Newton and by Leibniz and by, Fourier, among others. All sorts of mathematicians of the 17th and 18th century and so on. This is the kind of mathematics they did. And it was only afterwards, in the next century or so, that other mathematicians came and kind of, Cauchy, I think, I'm trying to remember who else there were, that kind of came and made it all totally rigorous, made all the theorems totally solid, using things like the mean value theorem in particular, and things that we learned last semester. So that's the way to make this into a rigorous a rigorous proof. I'm giving you a kind of a hand-waving proof. It gets the germ of the idea, it gets the idea, but it doesn't dot all the I's. So this is all done in my kitchen. I kind of liken it to painting a kitchen. You can paint a kitchen and do 95% of it or 98% of it beautifully, but doing that last little bit of trim takes a whole lot of work. And so we're going to do the 98%, get the idea across without all the work that it takes to put the final trim on. Okay, so here it is. So this is the idea. Here's what we do. We say, well, the length of this curve is going to be approximately what you get by adding up all of these hypotenuses. Is that the way to, the plural of hypotenuse? Hypotenuses of triangles. So each one of them looks like this. Like so. So that's approximately equal to that. And now, before I go ahead and take the limit, which is what you do now, you take the limit as delta x goes to 0, same as we've done before. I'm going to do a little bit of algebra here. And I'm going to factor the delta x squared out the back and write it as 1 plus delta y over delta x, quantity squared, times delta x. Do you agree? Algebraically, you can do that. You factor that out the back, and it becomes a delta x. If you bring it back in, it comes in as delta x squared, and you get this back again. So now we're good with that. So now I'm going to go ahead and say, since this is true, the actual length is equal to the limit of this thing as this delta x goes to 0. And as it goes to 0, the same thing happens that has happened in the past. We replace the summation sign with an integral sign, integral from a to b. And this is going to become 1 plus, there's dy over dx, because this becomes, in the limit, it becomes the derivative. Instead of the difference quotient, it's going to be the derivative at a point. And then this is times dx. So there's the magic. And this, again, this is the magic that Leibniz's formulation of the derivative kind of helps us do very naturally, okay? You just, this is his big contribution to calculus, is this notation. It just leads you in the right direction. So you can write it like this, or finally, if you want to, you can write it like this, right? We have the derivative there. This is, oops, I'm sorry, this should be the derivative squared. The derivative squared, and so the derivative squared. And there you are. So there's the formula. So here's the length. Length is equal to, isn't that cool? I love teaching this stuff because you just get these beautiful results just by using a nice intuitive argument. And there's the power of mathematics right there, of calculus in particular. So there's the formula. So let's go ahead and use it. Let's first use it on the problem that we've already done. What was that again? It was f of x is equal to 5x plus 1, where x was between 1 and 3, I believe. Is that right? And so that was this line like this right here. And so what does this formula say? It says the length is equal to, it's going from 1 to 3. So from 1 to 3, and then it's the square root of 1 plus the derivative. Well, the derivative of this, of course, is just 5. 5 squared is 25. And then you have dx. And now this is the square root of 26, which is a constant. You can bring it out the front. And then you just have 1 dx. The antiderivative of 1 is just x. Evaluated from 1 to 3 is going to be 2. So there's the same answer we got before. Okay? So there you go. All there is to it. Of course, if you could only solve a problem like this, it doesn't give you any advantage over what we had previously, but the nice thing is we can solve problems that we couldn't do before. Here's the problem though. We need to be able, in order to be able to do it, in order to be able to use this formula, look at what you're going to have to do. You're going to have a function that you take the derivative, you square it, you add 1, and you take the square root of all that, and then you still need to be able to find the antiderivative of this. If you can't find the antiderivative, you could use different methods of approximating integrals, which there are lots of them. But if you're going to do it exactly, you need to have a function that you do all this stuff to and still can find the antiderivative. So really, to be honest with you, there are only a few that are kind of easy to work with. Here's one of them right here. F of x is equal to x to the 3/2 power. Okay, that looks kind of like a parabola. It has its same general shape. It's concave up. And let's say we want to go, I've got it written down here. Say we want to go from 0 to 4. Okay, so we want to find that length right there. So what do? Well, let's see. It says we first take the derivative. That's easy enough to do. The derivative is going to be 3/2 x to the 1/2 power. And then this formula says now we integrate it from 0 to 4. We're going to have the square root of 1 plus the derivative squared. If I square this thing, I'm going to get 9/4 x to the first power dx. Agreed? That's what we get right there. I think that's right. And now we have to integrate that. How do we do it? I think this is a case where we can make another substitution. We can let u be equal to 1 plus 9/4 x. du is going to be 9/4 dx. And let's see once what happens. It's going to become the square root of u. That takes care of all this stuff. dx is going to be 4/9 du. So here we can put the 4/9 out in front. There's our du. We need to change the limits of integration. When the dummy variable here, x, is equal to 0, u is going to be 1. And when the dummy variable here, x, is equal to 4, u is going to be what? 4 over 4 is going to be 1 times 9 is 9 plus 1 is 10. So it's going to be 10 right there. So now I'm going to do 2 steps in one. This is the same as u to the 1/2 power. So the antiderivative of that is going to be u to the 3/2 power times 2/3. And we already have a 4/9 in front there. Okay, see that? So I've got my 4/9. Antiderivative of this is going to be u to the 3/2 times 2/3. You got that? And now you evaluate that from 1 to 10. And so it's going to be 8/27 times what? 10 to the 3/2 power minus 1 to the 3/2 power, like so. Okay, or if you wanted to, I would write it like this maybe. 10 times the square root of 10 minus 1. There you go. Okay, there's the answer. Okay, as I say, this is one particular problem that you can do this way, and I took this and I came up with my own problem, which I think it's a little more interesting. And this is one that I have my students do as a hand-in homework problem. And so since they are going to be watching these videos, I'm not going to show you how to do it, but I will tell you what the problem is here and let you do it on your own. Okay, here's my problem. It's one of my favorite ones I've come up with over the years. Here you've got yourself the curve y is equal to 2/3 x to the 3/2. Okay, so it's actually a little nicer than the previous one because when you take the derivative, you're going to get just a 1 right there. See that? That's why I made that choice. And here's the problem. You've got Al, who is walking along this curve, and you've got Bob, who is walking right beneath him. Okay, so Al is walking along this inclined path, and Bob is walking right beneath him. And the question is, obviously, since he's walking in a straight line, he's walking along a curved line, Al is going to be walking farther than Bob. And so the question is, where will Bob be when Al has walked exactly twice as far as Bob? Okay, so find Bob's position, his x-coordinate, when Al has walked twice as far, exactly twice as far as Bob. Okay, it's a beautiful problem. It can all be, it uses some you end up having to use a quadratic formula for it, and it's kind of nice. So I'm not going to give you the answer, but I think it has a square root of 3 in there, if I'm not mistaken. So see if you can figure it out on your own. So there it is. Okay, so there's that one. Okay, now as I was going to tell you, there are other functions that also have a property that when you take the derivative and square it and add 1 and take the square root, you can still get yourself something that you can integrate. Here's just a couple of them that I've picked up from textbooks over the years. So I'm going to write these down. I'm not going to do them. I'm going to leave these for you. So here's f of x is equal to x squared plus ln of x over 8. There's the function. And I want it on the interval x on the interval from 2 to 3. Okay, so find the length of the graph of this function on this interval. And here's one other one. I'll call this one f as well. F of x is equal to x cubed plus 1 over 12x. 1 over 12x. Okay, and here x is on the interval from, I have it from 1 to 3. Okay, so try those two. They work out. You have to remember squares. I guess this is the key to them. I'll just give you this as a hint. A plus b quantity squared is going to be a squared plus ab plus 2ab plus b squared. Okay, kind of have that in mind. Also have in mind that a minus b quantity squared is a squared minus 2ab plus b squared. Okay, there's your hint. So with that hint, see if you can do those two problems. Okay, so the next thing, let's see what time it is here. Okay, the next thing I want to do as part of this video is to also talk about parametric equations. In fact, I think this is enough of a good new topic. I'm just going to wait with this one and hold off for the next video. So I'm going to stop this one right now, and then we'll get into parametric in the next one. How does that sound?